Hello, I welcome you all in this presentation related with the subject fundamentals of surface engineering, and we are talking about the surface properties which are important from the friction and wear point of view. Under this heading we have talked about the two important properties. These were the surface energy and the chemical composition or surface composition. After that we had started the surface microstructure, under which we have talked about the phase structure related aspects. In this presentation initially I will talk about the grain structure related aspect of the surface microstructure, and thereafter I will take up the role of the surface hardness and the surface roughness on friction and wear. So, as we have seen that the microstructure of any material comprises the two aspects. One is the phase structure, which indicates the type of phases, the relative amount of the various phases which are present, and their distribution, where they are present, like whether they are within the grain or at the grain boundary, or the kind of whether they are at the surface or in the core, or there is continuous variation. So, it is about the distribution. Another aspect is the grain structure, which indicates the size of the grain, shape of the grains, and the distribution. Distribution means where, which type and the size of the grains are present, with at the surface which type of grain are there, and at the in the core region which type of the grains are present. So, because the both phase as well as grain structure are important from the mechanical properties point of view, which in turn affect the tribological behavior of the surfaces, determining the life of the component. So, it is important to look into the microstructure related aspects of the surfaces. So, as far as the grain structure is concerned, as I have said, it involves the average size of the grain, shape of the those grains or the micro constituents present at the surface, and these two aspects actually affect the surface energy, yield strength and hardness of the material, and cracking tendency at the particle matrix interface. We have seen that the higher the surface energy of the material, greater will be the wear and the friction. While on the other hand, the yield strength of the material and the hardness, both these are the mechanical properties and affect the surface deformation tendency under the wear conditions. So, these will be registering the plastic deformation of the material under the tribological conditions. On the other hand, there is one more aspect which is influenced by the grain structure, is the cracking tendency of the particle matrix interface. What is that? This is the matrix, and in which various second phase particles are present, like few needle shape and a few polyhedral shape. So, there is always a stress concentration at the particle matrix interface as per the geometry of these constituents. So, those which are the particles or the second phases which are of the high aspect ratio, higher aspect ratio means the needle shape structures, they will be offering the greater stress concentration at the particle matrix interface, especially near the tip, wherein the cracking tendency will be high because of the higher stress concentration, as compared to the other cases where the particles are of the spherical shape. So, greater is the cracking tendency, easier will be the possibility for formation of the debris, wear debris, and removal of the material from the functional surfaces. So, as far as the quantification of these aspects are concerned, like the size of grains. Size of grain, for this purpose basically we determine the average size of the grain, because different grains will have the different sizes, and rather there will be a size range. So, it will be appropriate to determine the average size. Now, as per the shape of the grains, there are different ways to characterize the size of grain. Say for example, in case of the cellular structure, it is the intercellular space which is used to characterize the size of grain, while in case of the dendritic structures like this, this is the primary dendrite, and when we see the branches like this on the primary dendrite, these are the secondary dendrites. So, spacing between the secondary dendrite arms is characterized as a grain size in case of the dendritic structures, and the same is the criteria which is used for the equexed structures, where the spacing between the arms is used to characterize the size of the grains. Apart from these matrix material structures, there can be various other structures like the needles. So, in case of the needle, we can measure the length of the needle is primarily used. So, if there are needles of the various sizes like this, then average length L1, L2 and L3, average of these three will be used to characterize the average length of the needle. Similarly, for spherical shape particles, it will be the average diameter of the spherical or circular shape particles that will be used to characterize the size of the grains. Now, if the shape of the grain is very irregular like this, in that case, to quantify, using the image analysis, we can determine the area of the grain like say this, and then we determine the equivalent diameter of this grain, and for that purpose we use A is equal to pi by 4 d square. So, here the d is calculated like 4a by pi square root. So, this is how we will be determining the average equivalent diameter, this is the average area of a particular grain. So, area will be used to calculate the equivalent diameter of the grain when the grain shape is very irregular. So, this is how the grain size is determined. Similarly, as I have said earlier, the shape of grain is characterized using the two parameters. These are called aspect ratio or form factor. So, for both we use the length to width ratio of a particular constituent, whether it is the particle of particular regular shape or the needle shape. So, in that case, the length to the width ratio is used. What is the maximum length and width of the constituent, that is used to characterize the aspect ratio. So, greater is the aspect ratio or the form factor, greater will be the nedularity or a needle shape structure as compared to the spherical or circular shape micro constituents. So, these were the about the size and the shape related aspects, and both these have significant effect on the since the grain size and shape have significant effect on the surface energy and the yield strength, hardness of the material and cracking tendency, which in turn determine the determines the friction and wear behavior of the material. Now, in order to see that how the average grain size or grain size is related with the mechanical properties, so there is one very commonly known relationship, that is called Hall patch relationship, which indicates that sigma y is equal to sigma naught, means this is the yield strength of the material of the single crystal plus k by square root of the d. So, indirectly if we see these and these two are the constants. So, yield strength of the material is found proportional to the square root of the diameter. So, decrease in the diameter of the grains or a reduction in grain size will be increasing the yield strength. So, this is a simple relationship, since under the external load conditions, surface layers especially will have tendency to get deformed, and if the material is having the higher yield strength because of the finer grains, then it will be showing the greater resistance to the deformation, greater resistance to the metallic intimacy. So, this in turn will be reducing the friction as well as the wear rate. So, both will be improved, especially under the adhesive wear condition. If we see this relationship between the grain size, means the grain refinement in increasing the d raised to the power minus 1 by 2. So, means this is in the order of decreasing grain size. So, this reduction in grain size increases the yield strength up to a limit, which is maybe like say the 10 to 20 nanometer, and thereafter further reduction in grain size has the adverse effect on the yield strength. This is what we can see. In the initial stage of the reduction of the grain size, the deformation is facilitated through the dislocation slip, and by this mechanism, when the deformation takes place by this mechanism, reduction in grain size increases the yield strength, while the further reduction in grain size starts decreasing the yield strength because of the because the grain boundary sliding is facilitated. According to the Hall patch relationship, in general, decrease in grain size increases the resistance to the movement of dislocations over a longer distance, which in turn increases the resistance to the plastic deformation. And since in hardness test also there is a sidewise flow of the material, and if the flow of the material is resisted, then this in turn will be leading to the reduction in size of the indentation, and which in turn will be showing the greater hardness. So, in general, increasing yield strength shows the increasing hardness of the material. Since the hardness is closely related with the abrasive and adhesive wear, therefore, it is important that grain size is properly controlled, so that required yield strength and the hardness can be realized. There is one other aspect like in a material which is having the matrix, and in the matrix we are having the few fine and few very coarse particles. So, in case of the coarse particles, the nucleation of the crack at the particle matrix interface becomes easier as compared to the case when the particle size is fine. So, the stresses required for nucleation and growth of crack at the particle matrix interface, that increases in case of the fine size or small size of the micro constituents as compared to the case when the constituent size is very coarse. So, when we have the fine grain size, it will increase the resistance to the crack nucleation and growth, and which in turn will be increasing the removal of the material from the functional surfaces, and so the wear resistance is improved, which in turn increases the life of tribological life of the component. So, refinement of the grain structure is needed. You see, whenever the grains structure is refined, it requires higher stresses for nucleation and growth of voids at the particle matrix interface. Thus, the grain refinement improves the fracture toughness and the wear resistance. This is what I have explained with the help of this diagram. If the particle size is large, it requires lower stresses, lesser stresses for nucleation of voids and their growth as compared to the case when the grain size is fine. The shape of the grain is another aspect of the micro constituents that significantly affect the stresses required for nucleation of the crack and their growth, especially under the adhesive wear conditions. As I have said, there can be normally the matrix, metallic matrix shows the certain types of the grain shapes like columnar cells, dendrites, equexed, while the second phase particles show the shapes like needles, spheroids, sphericals, nodules, polyhedral shape, star shape, Chinese script shape. So, and each type depending upon the shape, which is characterized through the form factor or aspect ratio. Depending upon the aspect ratio of these shapes, they will have the different effect on the tendency for nucleation and the growth of crack. In general, higher is the aspect ratio, higher will be the cracking tendency at the particle matrix interface. So, which in turn will be increasing the wear loss from the functional surfaces. So, influence of the morphologies of microconstituent on the wear is primarily determined by the way these morphologies affect the nucleation tendency, crack nucleation tendency, and the growth and their growth at the particle matrix interfaces. So, spherical particles will have the minimum stress concentration at the particle and matrix interface. So, it will resist the crack nucleation and its growth effectively as compared to the case when there is needler shaped particles at the particle matrix. So, in that case the crack nucleation and growth will be easier. So, such cases the wear rate will be high as compared to the another case when there is fine and spherical shaped particles are there. So, it is always preferred to have the fine and spherical shaped second phase particles as compared to the large and needle shaped particles. So, we need to actually alter the surface morphologies in such a way that they are fine, well distributed and largely of the circular family. In general, needle shaped sharp tipped acicular grain morphologies are found more prone to the cracking cracking and void formation than the spherical and round tipped shape microconstituents. Therefore, modified surfaces, if they are having the needle shape sharp tipped microconstituents, then the wear rate will be high as compared to the other morphologies. Form factor is used to define, as I have already said, form factor is used to define the ratio of the length to width of the microconstituent to characterize the shape and morphology of the microconstituents. We can see there are certain morphologies, these are the high sphericity morphologies and these are low sphericity morphologies. And if we see here this one is very angular, while this side the tip is rounded. So, aspect ratio of the low sphericity and angular particles will be greater as compared to the high sphericity and rounded shape particles. So, these are the two different aspects, like we may have the needle like this having the angularity is more, roundness is less, but there can be another possibility where we have the spherical particles like this with the reduced angularity, increased the roundness. So, increased sphericity and roundness will be reducing the stress concentration at the particle matrix interface, and which will be leading to the more favorable situation with regard to the resistance to the crack nucleation and their growth under the means tribological conditions. So, now this is how we can see even the microstructural, even at the microstructural level, size of microconstituents and the shape of microconstituents and their distribution affect their mechanical behavior and the friction and wear behavior. Another important aspect is the surface roughness. So, surface roughness is what another parameter which is another surface property which is important from the wear and friction point of view is the surface roughness. So, what surface roughness is? Surface roughness indicates the extent of ups and downs which are present, or extent of irregularities which are present at the surface, or extent of asperities which are present. So, if we see here, ups and downs are very limited. All real surfaces will have such kind of the irregularities as compared to the case when ups and downs are of this level. So, if we quantify these two roughnesses, here we may find Ra of the 0.5 micrometer and here it may be 1.5 micrometer. So, there is a Ra simply indicates the extent of the ups and downs surface irregularities or asperities, or what we can say peaks and valleys are present on the surface. So, greater is the roughness, means greater will be the surface irregularities or asperities will be present, higher will be the peaks and deeper will be the deeper valleys will be present on the surface. And why it is important for having good control over the wear rate as well as having the low friction coefficient, it is important that surface roughness Ra is as less as possible, but not very too high finish is also needed, because that in turn starts increasing the friction. So, an optimum level of the Ra is important, and like say the 0.01 or 0.1 Ra, a micrometer Ra will be excellent surface roughnesses from the tribological performance point of view. But if considering that most of the manufacturing processes, although depending upon the kind of manufacturing process being used to make a particular component, the different kind of the surface roughnesses can be there, like all machine components show roughness varying from like say 0.4 to like maybe 3 or 4 micrometer also, which is too high, while the cast components results in like maybe 2 to 50 micrometer. Ra 50 is for like sand cast or very coarse sand cast, and very fine die cast components. So, depending upon the kind of manufacturing processes being used, the roughness. Similarly, in case of the forming based methods, like whether it is cold will be having cold forming methods will be showing the lower Ra values as compared to the hot forming based method, they will showing the higher Ra value. So, what if there is kind of a particular kind of the roughness is present, and why it is important from the wear and friction point of view. So, the Ra is important, why? Because whenever the surface roughness is present on the real component and the two are brought in close contact with each other during the sliding, in that case these peaks and valleys come in contact with each other and try to have the mechanical interlocking, and when the two come very close, means two peaks and valleys come very close to each other from both the matting components, they form cold bond. The cold bond is formed and due to the relative motion between the two, there is always some kind of near surface layer deformation. So, which facilitates the work hardening of the surface layer material. In that case, out of the two matting components which are in relative motion with each other, whichever is weaker, the removal of the material or removal of the debris from that zone takes place. Say these are like 4 or 5 cold bonds have been formed. So, to maintain the relative motion, these bonds should be broken. So, these bonds can be broken from the interface or from any of the two sides. So, whichever is weaker. If the bond is weak, then the fracture of the bond will be occurring. Otherwise, removal of the material from one side will be occurring, whichever is weaker. So, whenever the metals come in direct metal to metal contact, cold bond is formed due to the mechanical interlocking, followed by removal of the material from one side, and that material whatever has been removed from one or other side, that finally will be removed in form of wear debris as a loss of material from the functional surfaces. So, in this case, if the surface is very rough, then the area of the bond is large, and so it requires greater force to maintain the relative movement. So, as compared to the case when the finish is too high, means roughness is very low, then the cold bonding will be taking place over a smaller area, cold bond area will be very small. So, to maintain the relative movement, the force required for breaking of such kind of bonds will be less, and therefore, friction will also be less. That is why whenever finish is increased, we find that friction force is reduced because of the reduced possibility for such kind of the cold bond formation or mechanical interlocking tendency. This is one aspect of the surface roughness where mechanical interlocking will be affecting the friction as well as wear. Greater the mechanical interlocking and cold bonding, greater will be the friction, greater will be the wear tendency as compared to the case when the limited size of the cold bonds or bond area is formed. Another aspect is that out of the two matting components like this, one will be hard and another will be soft. We do not use the matting components of the same type. They will always, the design is always made in such a way that the two are different for good wear and friction performance. So, out of the two, one will be hard and one will be soft. There should not be much gap between the two, but anyway, if one is too hard, so if the hard component having the too high roughness, then these peaks will be acting as a abrasive particles or indenter. So, such kind of the peaks which are present on the hard surfaces, they will be indenting the soft surface. Such kind of indentation will be leading to the formation of scratches and abrasive marks onto the soft surface. So, the peaks present on the rough surfaces will be acting as a abrasive particles or indenters onto the soft surfaces, forming the indentation and removal of the material by scratching. So, this is another aspect that if the hard surfaces are having the greater roughness, then they will be increasing the loss of material by abrasion. Another aspect is that whenever the surface roughness is too high, high surface roughnesses will be if the roughness is too high, then there will be presence of the peaks and valleys. So, these valleys especially act as cracks, fine cracks, and so in all those conditions like under the surface fatigue, wear, stress, corrosion, cracking, erosion conditions where impact is involved, cavitation conditions. So, in all those conditions where impact is involved or the forces onto the surface will be acting at a regular interval, the high depth valleys will be acting as a crack, and these will be facilitating the growth of crack easily for removal of the material. So, surface roughness, if the roughness is too high, it can act as a stress concentrator, and especially at the location of these valleys, and if the stress concentration is too high because of the high surface roughness, then under the surface fatigue, wear conditions, erosion conditions, cavitation conditions, the rate of material removal will be high. So, it is good to control the surface roughness, especially if the component is subjected to the conditions where the stresses onto the surface will be acting at a regular interval. Now, another aspect is about the the next important property is the surface hardness, which is very important from the wear and friction point of view. Very smooth hard surface results in the lower friction and reduced wear, both abrasive and adhesive type. There is a very famous Orchard's law on the adhesive wear, which says that the wear is inversely proportional to the hardness of the material, inversely proportional to the hardness of the material. So, greater is the hardness, greater will lower will be the wear loss from the material. Similarly, the hardness also affects the abrasive wear, because in case of the abrasive wear, abrasive particle or indenter should indent the surface, and then due to the relative movement one sketch will be formed onto the surface for removal of the material. But if the hardness of the material is high, then the depth of indentation is reduced, and accordingly the volume of the material being removed by the scratching or abrasion, that will also be reduced. So, an optimum level of the hardness is good for both abrasive and adhesive wear. If it is the only abrasive wear, then hardness should be high, but if it is the adhesive wear, then combination of the hardness and toughness is important, while under the conditions of erosive wear, and the cavitation erosion conditions, it is important that a good combination of the hardness and toughness is maintained, so that surface can remain coherent and the material from the functional surface is controlled. Now, I will summarize this presentation. In this presentation, basically I have talked about the role of the grain structure on the wear and friction behavior of the material, the role of the surface roughness and the surface hardness, and how these surface characteristics can be related to the wear and friction properties. Thank you for your attention.